this lecture gives an idea of how you can use UNSW that means our developed near-whitened fly ash in virgin white polymer polypropylene. Now, fly ash has some carbon, and what is that known as? It can vary from 1 to 3%, and in some cases LOI. So, if it's burnt, if the fly ash is heated in a furnace, then that the carbon can disappear, and it can make the fly ash more white. So, normal fly ash can be used in many applications, but there are times when if you have a white product, it reflects more light. So, for example, if you are wearing a colored shirt, you need more light to be seen, but if you have a white shirt, even with less light, so if you don't want to be seen, then it's better to go for a colored shirt, but if you want it to be seen, then it's better to go for a white one. Now, polymers generally have white color, or transparent or semi-translucent or white color. So when you make things like that, they are quite white in color. But if you put fly ash in them to make them strong, then often the color changes. Ahmadzani was my former PhD researcher, and UP Singh, he came to our university together with 3 other colleagues of him and the Deputy Director General of CBET, Chennai. So when this team came there, we organized a 2 weeks very intensive course, and then also I wanted them to do some project, each of the 4 participants. He's a scientist. I think he's still in Chennai. He was earlier in other CBET, but then he moved to Chennai. So we know fly ash is fine powder collected as residue in the exhaust gases from combustion chambers of pulverized coal-fired boilers at power plant stations. So this is what fly ash is, we know that. And this is the typical morphology of fly ash. You can have spherical fly ash, and you can also have irregular shaped fly ash. Both of them are shown in the same scale bar. This, from here to here is 30 micron in the picture, and then, all right, so the fly ash morphology is spherical and also irregular. And we know, we have seen this slide, similar slide, like agriculture, cement, concrete, polymer composites, and then if you press the next slide, then the polymer comes again, and we have seen this polyethylene, polypropylene, polyester, epoxy, and other polymers. Polypropylene, not many people have used, but we have used in polypropylene, and this came, the use of polypropylene, how it came, a company, they actually gave us some used polypropylene, polyethylene. They gave us some polyethylene which has been used from car bodies and things. They've been broken into small parts, and then they gave it to us. So it's recycled polyethylene and recycled fly ash. So then we have used that. That will be part of another lecture later. And then polypropylene we have shown. Polyester we have not done work, but other people have. And epoxy we'll show later. And also you can use in other polymers to get different types of properties. And like Professor Kamalkar, he went through, there is no end of properties. and also at the same time there are limitations on properties, whether mechanical, electrical, then dielectrical, magnetic, and all those things. The fly ash has so many components which other materials do not have. If you have a ceramic, normally you have a single ceramic, but in fly ash you have so many types of materials, oxides. Okay, so you can select fly ash, or you can remove some of the aspects. Okay, so fly ash, I call it fly ash and engineering gold. All right, and I proved it to the Campus Review Australia, who actually examines all universities and tertiary educations in Australia, their research and things. And about 4 or 5 years ago, they decided to select some researchers, and they put me as one of the top 5 in the materials research area, and then one of the top 5 in the entire Australian education. And because that was my work in converting fly ash into near-whitened fly ash. Okay, but because they are not all engineers and ceramics, so it took them about 1 month, and every day I used to receive email from them, and they had lots of question. So I had to keep on answering them. But again, one of my thing is that if you can answer so many questions through so many journal papers, sometimes it becomes simple if you send them a few compositions. Okay, so that is what I did when ECUFA conference was being organized in Kolkata, the Pollution Control Board International Conference of Utilization of Fly Ash, either people from all over India and also outside India. And I happened to be the suggestion. And then just the night before the conference, I said, hang on, people will come. And then something came up in my mind. Like I said, fly ash from coal power station. That came just at midnight before the conference, and I sent it to the chairperson by email. But then I had to do the same thing. I had to send the same thing when I found the editor-in-chief of that this Campus Review Australia going deep and deep, and then I said, look, this is something which would you like me to send it? And I sent that one, and that made it much easier for the person to understand. So sometimes simple language is very useful in transmitting information. You can make it as complex as you like. It can go into very deep, but even if you can make it simple and easy whenever presentation, so it just goes into the minds. Now, in composite-based products with range-rich mechanical properties, the strategies are new experimental condition, screening of polymers, addition of additives. And here, in our case, in the fly ash, utilization fly ash, this is what we undertook, modification of fly ash. Fly ash is, like as one of your friends said today, that coal particles can cause a lot of health problems, fine coal particles. Now, fly ash can also do that, but fortunately, fly ash is not sprayed into the air, it's collected after the combustion, all right? But we had a chat with him, and that's a different thing, but each issue can be handled. Now, so far the response of producing polymer composites using fly ash has been stiffen the matrix, that means make it rigid, lower cost of material, as Professor Kamalkar always says, all right, and that is useful. Modify rheological properties. Rheological properties is flow properties, how the material, it flows under stress. Now, sometimes we think rheology is related to, most of the time, liquid or semi-liquid materials. But you can also consider rheology as the property of the molecular chains, flow property of the molecular chains. So that can happen also in the solid state. Increased strength of the polymer. We have focused these aspects. And then surface morphology, chemical composition, color measurements of several fly ash samples. This is what I shown one of the slides, I think, yesterday. And as I mentioned, we use the equipment in the optometry section. So that shows that how fly ash particles can actually, different fly ash products can give different color. Because optometrists, you have courses in optometrists in India? There must be. Because optometrists are a combination of science and engineering. They are a very useful course, okay? Very useful course. Now, we developed a method to modify the color of fly ash from gray-black to almost near white, to 96% whiteness of calcium carbonate and also 95% whiteness of barium sulfate. And it was believed that this will assist the fly ash recycling industry to make better decisions regarding use of fly ash, so far as the color effect of the fly ash products is concerned. Now this is what the result of our research. Okay, bottom part, hang on, someone has come to, is asking, he said, come and give me some fly ash. Okay. Good. I think this feature wants to change its color from brown to white, so I said, please give me some fly ash. Okay, I'll give you, but we've gone. Now the bottom one is 100% polypropylene sample, compression molded. And this is one, if you are using the normal gray-black fly ash, you put the gray-black fly ash. Gray-black is good, that Professor Kamalkar showed a bottle the other day. That's typical gray-black fly ash. It has some limited carbon and it does not have much of browning agent, okay? So if you put that one in a polypropylene, white polypropylene, then the color changes to something like that. But then, instead of putting the gray-black, if we modify the gray-black and we remove this carbon from the gray-black, and it becomes near white and fly ash, then if you put it back, then it becomes very close to white. Now, whilst we did this work in polyethylene, but as I had mentioned earlier, I think there is also a huge scope of application of using such things on the road surface. In one of the tutorials later, we'll show how the road surface can be modified. Now, road surface, you have pitch, and in the daytime it's all right. But when it becomes night, and particularly if it rains, the road surface can become very dark. And then it can be a bit unsafe, okay? But if you can, and it happens in Sydney also, where when I drive at night, and I say, hang on, when it's raining in the evening, the roads all becomes very dark. Dark means you cannot see the roads clearly. But if you can use some fly ash, and fly ash is a ceramic, so it's not a weak thing, okay? If you can use in addition to this pitch and other things, then it can actually help people and it can reduce accidents. These days, in our state of New South Wales, where Sydney is the capital, almost every week, or why every week, every day or every second day, in the TV, we see lots of road accidents. Not only motor cars, big trucks, they just, so I have a feeling that one of the things is that the visibility of the road becomes much less, particularly in the evening. Yes. So I've tried to inform the governments about using this near-whitened fly ash, but the ministers do not receive all the information. It goes to the staff, and sometimes it goes into white rubbish bin box. All right? But one day it will come up. And I thought in here, well, if I can pass on that information, so I'm sure if you can use it, it can be very safe for passengers and drivers and also pedestrians who are walking. So if I ask you, this is 100% polypropylene, this is polypropylene plus near this normal black, gray-black fly ash, and this is, if you whiten the fly ash, remove this residual carbon, it becomes pretty close to that, isn't it? So this one, you can see much, it has a lot of visibility, almost white in color. And of course, then you can measure the whiteness by using equipment, all right? So you can give a feature to that. So this one, you remember the fly ash that Dr. Kamal Kar brought in a bottle. I didn't bring any fly ash from there because sometimes when you are traveling and you are in the security area in the aircraft, they sometimes do not allow. And if you take it in a handbag, they might take it out and throw it away. Or if you put it in your suitcase, all scattered on, the X-rays and everything they do. And when you are in this, they might remove the suitcase from you. You are here in Sydney, but the suitcase goes back into, not in Sydney. You are here in India, like Kanpur, and suitcase goes back to Sydney, something like that. These things are happening. Security has become very strict. I'll give an example. I bought a laptop because I don't use much of iPad. So I bring laptop, and every time I come, we put the laptop in one of the big suitcases. This time, when we are we put the suitcases, before they send the suitcase to the place to be uploaded in the plane, the guy in the terminal, they said, "Do you have any computer there?" I said, "Yes." "Does the computer have a battery?" I said, "Yes." And this is what I always do, 100% fact. Don't hide anything because it's for safety of yourself and anything, all right? That's my policy. That's people like me or not, 100% fact, true fact. That's what I do. And then it said, "Sir, you have to remove the suitcase." And my wife was there, and she said, "Oh no." Then I said, "Look, take it easy." And my youngest daughter also came with us. So they opened it and all the things. And I put it in my handbag, okay? Now, I said, "What happens?" But then I said, "It's all right." Now, here they will see, and if they have any comments, but then they checked it using all this scanning and things. They said, "That's all right, you have battery." But these things can happen anywhere. Is so important, but I agree with them, because if you have a battery there, if the battery collapses or something like that, and you have things, all phenomena, if sometimes under stress or under pressure or under load, under flow, shear flow, if something happens to the battery, if the battery creates a fume or a flame in the suitcase, then it might. So these are the things. This is what I like about all this latest security technology. And even they use FTIR and things. And when sometimes they call me and they said, "Are you scared about this technique?" I said, "No, you can do as much as you change, all right? Or as much as you check." So, because of all that, I could not bring any of the fly ash with me because I didn't want to throw them away. But good that Professor Kamalkar shows you an example of gray-black fly ash. So our fly ash which we used at the same color, and average particle size 8.3 microns, which is quite good because as we showed that typically up to 40 micron size it is good. So 8.3 is very good. And then this is the near-whitened. So when it's within 5% of calcium carbonate, that means it has 95% whiteness of calcium carbonate. All right? Or we also measured barium sulfate is a little bit more whiter than calcium carbonate, but again about 95 to 96%. So this looks quite white. So from here we change that, and that actually, if you go back, that changes the color of the composite from this to that. Now, selective fly ash modified to near white color opens a big new application opportunities. And I'm going through that slowly, and I would like all of you to do your best, okay, to use this in various applications. If you are a chemist, you can use in chemical applications. If you are a biologist, you can use biological applications. If you are a civil engineer, you can use road or construction application. If you are a mechanical engineer, or if you are a painter, you can use in painting applications. Okay? So fly ash, it can become very expensive things. If you do business in fly ash, you can sell it at a higher price. All right? But the purchasers may not like it, but at least now DST India has made fly ash a commercial commodity, so government of India will support you, but it will also give you some sources of income, and it will also make the coal these generators quite happy. Okay, in 2009 we submitted a standard Australian patent, and this is the application number. But this went on. It takes time there, even for provisional patent to go to the next stage. It takes 2 years, 2.5 years, 3 years, and by the time the researchers change and things like that. So that's, I cannot do much of it, but this is the number. And this is Dr. Upinder Singh. He came to, and this is our lab, our old building. We have changed to a new building. This is the injection molding, and I thought it's better that we put the injection molding. This is the injection molding, and this is the near-whitened fly ash. You put this polypropylene and the fly ash. And can you see that fly ash? It is all white fly ash, all right? So this is what we have developed by giving thermal treatment. And then, because he came from CPET, and he said he became very interested in working. So when I came here about a week or two ago, I sent an email to him and all the other people saying that we'll be having this thing. So I've not yet heard from them, but it may take more time. So he was there, and that is the near-whitened fly ash you can see there. And the specimens were made, and this is the commercial injection molding. Sri Badley is me, and S.K. Naik is the Director General of CPET, and he's at the moment Chennai. And I've been to CPET many times, and so we had a teamwork. So now, having made the samples, this is just normal light in the veranda. So this is the polypropylene. So it looks a bit translucent because this is a polymer, I think 3 millimeter thick. And there, we put 5% near-whitened fly ash, 15 like that, up to 58% near-whitened fly ash. And these are, what kind of specimen, what type of specimen is this? Tensile, yeah? Notched impact. Notched impact. So you can use for typically Sharpie iodide, okay? So notch impact is, from polymer applications point of view, notch impact is very important, okay? Because if you have a notch, that means it gives you a high stress concentration. So there is much less ductility, okay? You remember many years ago, this notch testing came up when many years ago, what is that ship which hit a ice block and just the steel fractured because the temperature was below the glass transition temperature of the steel. So since then, people say that, okay, generate these types of things and check it, okay. So now, PP is particulate. Yes. Yes. Yes, yes, yes. Yes, 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 yes. Because we want to make it as simple as possible. Actually, in one of the slides, let me. Did I mention where the particulate PP? No, it's not in this one. Oh, yesterday I showed. All right, thank you. Our professor from HBTI, she couldn't come yesterday, so if you can go back and check that, all right? Okay, thank you. This is polypropylene. PP. No. Okay, PP means polypropylene. P is okay. P is polyethylene. You can have high density HDP, low density. We'll get back to polyethylene later. Okay. No. If you have any question, always do that. I also yes, sir. Yes, we have checked that. Is that the carbon is gone? Yeah. Yes, because the main thing is, the main thing is carbon is so good for giving, but carbon also gives you a color. So that carbon disappears. LOI goes down very much. Okay, so this is a picture taken just in the veranda, because I said normally researchers like to do it under very strict conditions. I said, look, when you are manufacturing and things like that, they don't want to waste your time. The manager will come and take a look at it. So that is what the manager's eye is the microscope. All right? And you accept that. And then what I said to them, okay, turn them over. So this is the same samples. This is the polypropylene without any name. And then I said, put them in any order. So there's a mix. So you cannot say which one has 5% or which one has 10%, which one 80% or 60%, but they all look the same. Can you see that? So irrespective of 5 to 80%, irrespective of that, it looks very white. So if you have these things like this in the pitch, in the road and things like that, also, then it will become very, very good for the eyes. All right? So this is what we did. And why we made this test? Because tensile test, as you have seen there, tensile test, you get some values and things, but in the tensile test, because there can be local this factor, concentration factor, sometimes it shows lower stress with a higher percentage. In some other material, it shows higher stress. That tensile stress test is not that accurate. All right? Yes, it depends. So you also do tensile modulus. Then you also look at this strain to failure. And also you look at this impact. Impact is important. Compression test sometimes is much better. So from my experience, tensile test is not always a very valuable thing. Just don't only depend on that. Go for the modulus and other things. Okay. So this shows, if you go back to the earlier one, the sample is at 5% near-whitened fly ash, 10%, 15, up to 58%. And then when we turn them over, and I told my student to mix it, and here it says PP, polypropylene. I said, this is just in a veranda, and I said, now just look at it and put it in such a way that you get enough light. The same sunlight and daylight. There is no. So you can see that there is shadow coming up from there. But now they all look the same white. So which means if you make this thing, when you transfer the color of the fly ash, you don't always have to go for very high percentage. Whether you take 5, 10, 15, 20, it all gives you very good whiteness. All right? And that's what made this people also good. But then the Director General, he happens to be a polymer chemist. He will always ask you a question. And that's why instead of the tensile property, I went for the impact properties, okay? Because I sometimes think like the Americans, always think about the worst, all right? The Americans always think that don't think about the best, think about the worst and then make it better, because that's what I've been there. Now, I've lived in Australia but I've been American so many times. As a visiting professor in University of Delaware, as a visiting professor in University of Central Florida, I've been to defense labs. And when I was a visiting professor in University of Delaware, there, my host, Professor Richard Wool, is a very, very high quality professor. And what he developed, he was developing polymers for composites using soybean oil. So he had his team from different countries, his own university and different countries, chemistry. They were actually developing polymers like polyesters and things like that using soybean oil. Soybean oil is very, yes, and it is huge quantities. So when I also travel along the roads in America in different states, on the left-hand side, right-hand side, huge this fields where all this, and I just asked them, what are they growing? It's soybean. Soybean is hugely grown. So they said, rather than throwing away all those after they getting the soil, after getting the oil, can we use it? So Professor Richard Wool's team generated soybean, but they had this an industry which make all this building construction equipment, and so they like to use composites instead of steel as their structure because it will become very lighter. So they wanted to make composites and they wanted to work out the toughness of those materials. So that was one area where Professor Richard Wool, he thought I could help them. So I went there, I stayed for 3.5 months, and I generated all the results in the toughness of those materials. And then what they were surprised, and I was surprised also, by using polymers developed from the soybean oil, not the chemically, just converting it and using that as a matrix and then putting glass fiber in it, the fracture toughness became much higher than actually the plastic and the glass fiber things. So that surprised me also, but I was not keen, I did not understand the chemical bonding, things that I left to them. But at the same time, they did not understand how to measure and how to work out this fracture toughness, So I worked it out and they used my information. And after I came back and America is very quick in all this. Within 1 or 2 years, I was told that Department of Energy and other bodies gave Professor Richard Wool $10 million several years, many years ago, 10 million American dollars to go ahead with it. And he immediately opened a chemical company in his department. And he started going on with it. And that technology was then used to construct all this road bearing or earth moving and all these materials and construction materials, okay, because they becomes much lighter. And that also saved other products, and that also utilized the soybean oil, which is not used much now, and the soybean products. So that is something which helped him very much. And as I said, as soon as their products became so good, he was given a $10 million and he opened a plastic company in his department, in his university, which is known as Sarah Plastics. So I think Sarah is the name of one of her two daughters, most likely. But that was nice, so that his polymer research and this toughness measurements, so that combinedly generated this new class of materials. Nothing to do with the color. I mean, we are not worried about the color. But when we develop the plastics have normal white color. They are okay. But that's what I said. That's why whenever all these electronic things and like that, all this, they generated in America and they immediately go into production. I would like India to become something like that also. I think India is also doing very well. Okay, now is the result of the notch impact. So we didn't worry about the tensile and other things because, as you know, so without any fly ash, this is the polypropylene. This is the, I think, joules per meter square. And then when you go up to about 20%, you get about 25% improvement. But one good thing, none of the fly ash composites shows any more brittleness than the polypropylene. Can you see that? So even if you go up to 20% thing, so that means that sometimes people think that a ceramic can make a polymer more brittle, but it didn't happen. And that's what, as soon as Professor or Dr. Sanjay Naik saw this, he jumped up. He said, hang on, fly ash is a brittle polymer, fly ash is a brittle ceramic, all ceramics, and you put it in polypropylene, which is normally ductile, and you improve the toughness. I said, I didn't improve this. The near-whitened fly ash did that, so don't praise me, praise the fly ash material. Then he said, they would like to take it up. And then, and 25% improvement in impact fracture toughness is very, very, very good, okay? And then subsequently, he published also this work in one of the international journals where he was co-editor. And also CPET has a thing called CPET Times. If you go for CPET Times, it was published there in the CPET Times. And when I was given the CPET Times, I went onto the website, I was going through that, and all on a sudden I saw before my article, I saw the photograph of the great Dr. APJ Abdul Kalam. And it was so nice to see his picture before my article. Okay, so I can send you that website sometime. Now, scanning electron microscope of the fracture surface of 20% near-whitened fly ash. And not is fracture, this is impact fracture. I think it's like joules per meter square something. Yes, so they have different types of units, but yes, but basically the way I was looking at it, it gives whatever you have without the near-whitened fly ash, you get about 25% more. So the advantage is that the color remains white of all the samples which we have seen there. So this is the one which is a main objective. But then if you go to the strength does not always mean something, but when you look at the notched impact, I think sharp impact, okay, versus it. And 20% showed the highest value. That's why we took a look at. And they were Upendra Singh and the CPET people were there only for 2 weeks. And out of the 2 weeks, every week, they had to do a lot of work. So in between, so every day about a couple of hours, they could do this experiment, okay? So this is where there is percentage. This is 20%, the one which showed the highest amount of impact fracture toughness. And here, the mechanism of toughening is particle debonding and frictional pull-out energy. So some of the particles are debonded here from here and pull out. This is, write it on the board, debonding and pull-out is a very important mechanism of getting toughness. Debonding means you have the bond between the fly ash and the particles. If debonding means something is removing the bond, so that is taking up energy. And pull out means it is coming out, so there is a lot of shear force needed to remove the particles. So please make a note of this one. And this is, debonding is, let's say, energy 1, and pull out takes up lots of energy 2, and this is high shear energy, because it were, so they are bonded but they are not fracturing. So if you can, all of you can do it this way. You have your finger and then have other 2 fingers on that, press it hard, and then try to pull up these 2 fingers like that. And you have to, because if it's bonded hard, it's taking fair amount of energy. So all this impact energy you are giving to the material, so instead of it going through and fracturing the things, it's being used up in shear taking, okay? So it's removing the shear. So that's what is actually making the specimen much tougher. But if the debonding and the shear removal energy is very low, then it will take much less energy. So what is that? It goes to high thing because it's taking up that when you are doing it, it has to work hard to do that, okay? So that makes it useful. And also you can see here, can you see that the fly ash, can you see there is layer of polypropylene there? Because so there is bond to the fly ash, and then it came out, but it's shearing. So this is how, here another fly ash came out, but the other side. So there is a lot of shearing and debonding. So that is actually shearing, debonding, which is the pull out, that is taking up this energy. Now polypropylene and 50% near-white fly ash, you have high magnification, and there you can see that there is this is much higher magnification. It's only 2 micron, and here you can see even inside the holes where they're cracking, there's still a lot of bonding, and these are some of the things coming out, bonding. The fly ash particles are not cracking. Fly ash particles are not cracking. Rather that they are coming out and debonding. So there is good bonding and pull out and shearing. So that is what is taking up this energy. So this is some fly ash particle. This has the fracture surface where it's lots of particles. Although impact energy is often considered to be much less because you don't have any time for deformation. So, but the particles here in this case as the fly ash particle is giving up, taking up that energy, shearing, and this. So if something is coming and hitting the component, it has to come and hit with much more force to make it brittle, crack in a brittle manner at a lower energy. So bright end products. So when I say we, you can all do that. Use white-end fly ash in every broad aspect of engineering. And I'll come back to that. And we can revolutionize the use of in India, in Australia, and I would like all of you to think about it, all right? Because this is something which you can do in road and everywhere using paints and things like that. So if you have a near-white fly ash, it's so cheap, and you can develop systems which will take a lot less energy to make it, convert it to. So yeah, this man, I always remember him. Okay, what a great man, and what is such a polite man. So let's give our regards to him. So if I now go back to the very earlier slides. So your gray-black fly ash converted to near-whitened fly ash. So yes. You can use your own techniques, because you can use your own techniques. You can use heat and things like that, whatever way you do that. Okay? But that's how. The middle one is dark colored. If you don't need white things, don't worry about it. But this gives you a new dimension, new material. All right? I'll stop that. And thank you. Can you go back to my one earlier file from yesterday, which I didn't have time to cover, because one of the set of slides which the question was, how did they? This is not near white-end fly ash. This is normal fly ash. This is normal fly ash, and we asked the question, how does the impact property of that normal fly ash composite goes? And I'll see if it's there. Just wait for me. HBTI. Hello, HBTI. HBTI, Professor, come in. कल आपने ये पूछे थे, हम मुझे कल स्लाइड दिख रहे थे, जो polypropylene, normal polypropylene, normal fly ash, how does the impact strength go? So I had stopped because Professor Kaur was giving his, so here I put those slides back, and so please see that. This is the fly ash content, 100%. That means if you put 100% in 100% resin, so that becomes 58%. And this is the impact strength, which is here. So normally the impact strength is like this, about 1.5, so about 1.7 kilojoule per meter square. And then when you put this fly ash with about 20%, the impact strength goes up to from 1.7 to about 2.7. So if it goes up 1.7 to 2.7, it's about 30% increase, okay? And it still remains, even up to 80%, it still remains at quite high. So this is the impact strength is quite high. All right? So this was your question. Now, another thing which comes up here, with the addition of fly ash, the crystallinity of the polymer also goes up. Here you have crystallinity here, tensile stress goes down as we have seen that, but the crystallinity is this red one goes up. So from about 35% to about 45%, and the impact property never comes down below the polypropylene. And impact properties are very important and often the most important. And in many situations, tensile stress, it shows certain things, but tensile stress also can generate this localized stress intensity factor. That's why instead of tensile stress, even if you use low speed fracture toughness test, that is better than tensile stress, particularly for composites. If it's a single material, if you have only polypropylene, polyethylene and things like that, you can use tensile. So that's one which you had asked me the question, I said this answer, but I remember that I should show that one. Does it answer your question? So yesterday's general summary was that mechanical properties of fly ash, particulate fly ash filled polymer are dependent on the several factors such as composition, component structure and interaction, which can be improved by introducing a modifier. There are many theoretical models which describe the correlation between these mechanical properties with structural parameters, and it has been observed that existing models are inadequate in predicting the properties of composites. And this article suggests the existence of a new multidimensional relationship between the structural crystallinity and impact strength. Because impact strength, if you can improve, and as I said, when CPET director, when he went there and when he found that fly ash can actually use the impact strength significantly, and here the impact strength is increased, it never comes down to the, whether you are putting 20, 30, 40 or like that, it is always much higher than the normal impact strength. It goes up very quickly up to about 10 or 20, and then it slows down. This is the impact strength, but still it does not come down. Okay, thank you.